let's confront a seriously frustrating reality for you Cambridge 9702 physics students out there. Losing those super easy grade boundaries on crystal structure questions. I mean, you've read the textbook, you've highlighted all the definitions, and yet, when that paper comes back, the marks just aren't there. Well, today we are going to fix that by decoding exactly what the examiner actually wants to see. Let's get right into this explainer.
So rather than kicking off with some dry textbook definition, let's actually uncover a really painful but super common mistake. Why do students consistently lose marks on solid-state physics questions even when they've perfectly memorized the textbook labels? Well, the core issue is that students will state the correct terms but totally fail to explain the underlying physical phenomena. You're giving them the label, but you aren't showing them the physics. Examiners don't just want to know that you've memorized a vocabulary word, right? They want to see that you truly understand the microscopic mechanism happening inside that material.
Section 1. The 4-step answer framework. Engineering a perfect response.
To stop bleeding those marks, we need to completely overhaul how we approach these questions. To build a truly top-tier answer, you literally cannot skip these 4 steps. First up, state the core concept. Second, bring in the evidence or the data. Third, and this is absolutely crucial, provide the scientific reasoning. This is where you explain the why. And finally, step 4, lock it all in with precise examiner wording. If you structure your paragraphs this way, you naturally bridge that gap between a scattered list of random facts and a cohesive, top-band physics answer.
Now, to actually memorize this progression effectively, anchor it to 4 vital memory cues. Ask yourself, what is it? What changes inside the solid? What can be observed outside the solid? And where does this actually matter in technology? If you can answer these 4 rapid-fire prompts out loud, purely from memory, your foundation is incredibly secure for some intense revision. It perfectly represents the float from the basic definition, down to the microscopic mechanism, out to the measurable consequence, and finally, right into the real-world application.
All right, moving along to Section 2, inside metallic crystal arrangement, from macroscopic to microscopic. Think about a solid metal block in your hand. Why exactly does it bend instead of shatter into a million pieces? Why does it conduct electricity? The macro behavior that you can feel and observe is entirely 100% dictated by what happens internally, way down at the atomic or carrier level. Once we picture that everyday reality, we can then visibly tighten up our vocabulary into the strict, technical exam terms that are required for full marks.
Now stick with me here because I'll make you a promise. In just a moment, I'm going to show you the exact examiner clue that changes the answer completely. But first, you really need the framework that makes that clue super obvious. Leaving now or skimming ahead means missing a vital missing link that literally transforms a decent answer into a perfect one. So the absolutely crucial first step is grasping this exact definition. Metallic crystal arrangement is the specific spatial organization of atoms and carriers within a solid that dictates structural behavior, energy, transport, and field response. That's a mouthful, I know, but this is the necessary foundation in our sequence of mechanism, consequence, and application. Seriously, if you don't anchor your answer right here, the rest of your physics explanation just kind of falls apart. By comparing these structures, we establish some really strict boundaries. Take the metallic crystal arrangement versus a closely related concept from the very same chapter, like an ionic lattice, for example. Under the intense pressure of an exam, it is so incredibly easy to blur these microscopic topics together. You need to know exactly where the metallic carrier model ends and the rigid ionic lattice begins, so you don't get them confused and drop easy points.
Okay, Section 3, flawed versus perfect answers. Let's do a quick interactive challenge. I want you to mentally pause for a second and see if you can spot the errors here. A flawed answer is, frankly, just a scattered collection of facts. It might mention an application, sure, but it completely fails to provide any microscopic reasoning. It's basically just memorized labels. Now contrast that with a perfect, disciplined, top-band paragraph. A great answer rigorously connects the microscopic cause, the spatial organization in those carriers, directly to the observable macroscopic effect. That strict connection of cause and effect, that is exactly what the mark scheme demands. Examiners absolutely eat that up.
Next up, Section 4, real-world physics applications. Why structure matters. This is where the physics truly leaps off the page. To make this stuff memorable, we absolutely must connect our microscopic mechanisms to tangible, high-stakes materials. Look at aerospace turbine blades. They rely entirely on defect tolerance within the crystal structure so they don't, tear apart mid-flight. Semiconductor wafers depend on precise bonding directions to actually function in your electronics. Structural alloys and gemstones, they get their incredible unique properties from their atomic packing. You aren't just learning abstract dots on a page here, you are literally learning the engineering blueprints of the modern world.
All right, Section 5, the final examiner clue, bridging theory and data. Let's get into it.
So, we've mastered the theory, but here's that final examiner clue I promised you earlier. Here's the harsh reality. The theory is really only half the battle. Knowing the structure inside and out won't save your grade if you're faced with a complex data analysis question that demands you prove these concepts through a practical investigation. Examiners are increasingly linking the pure theory of crystal arrangements to experimental variables, graphing skills, and practical laboratory setups. You have got to be able to evaluate the data that proves these structures actually exist.
Which brings us to the ultimate question: how exactly do we design that practical investigation and analyze the linked data to prove this metallic crystal arrangement for full marks? This is a massive, unresolved problem, and it's exactly what you need to master next to totally ace your exams. So make sure to join us for our next explainer, where we'll break that down step by step. See you then!